Hey, welcome to The Explainer. You know, every major discovery, every single piece of real, solid knowledge, it all starts with a plan. Today, we're going to pull back the curtain on the scientific blueprint. This is the essential framework scientists use to turn a simple question into a powerful, reliable answer. So let's start with a question we've all probably asked ourselves. Does using your phone really make you a worse driver? I mean, we've all been there, right? You see someone on the road, phone glued to their ear, and you just know it's dangerous. It feels that way. But here's the thing. Going from a gut feeling to an actual fact, well, that takes a process, and that's exactly where a real scientific investigation kicks off. So to figure it out for sure, scientists can't just guess. They need a blueprint. Your gut feeling, my gut feeling, honestly, it's not enough, because it's just full of biases. That's why this blueprint is so important. It's a system, a structured way of thinking that's designed to strip away all those assumptions and guide you from that first spark of curiosity to a conclusion that, and this is the key part, anyone can test and check for themselves. All right, so let's get into the first part of this blueprint, the spark and the aim. See, every single investigation starts with that little spark of curiosity. But a big idea on its own is, well, it's just too broad to actually test. So the very first step in our blueprint is to take that big idea and boil it down into one single, clear purpose. And that foundation, that core purpose, is called the aim. You can kind of think of it like a mission statement for the entire study. It's just a clear, simple sentence that says, here's what we're trying to find out. That's it. It becomes the North Star for the whole project, making sure every single thing you do is pushing toward that one specific goal.
So for example, let's see how this works in the real world. You might start with a general question like, does defensive driving training actually help new drivers? The word help is, well, it's pretty vague, right? So we sharpen that into a specific aim to examine whether defensive driving training helps reduce the number of accidents. See the difference? We replaced a fuzzy idea with a super clear, measurable goal. And that's how you go from just a general idea to a truly testable purpose.
Okay, so once our aim is set, our purpose is crystal clear. The next piece of the blueprint builds right on top of that. Now we're going to make a specific, testable prediction about what we actually think is going to happen. This is what we call the research hypothesis. Now, if the aim is your final destination, think of the hypothesis as the specific route you're predicting will get you there. And it's not just a wild guess, not at all. It's an educated guess. It's usually based on what we already know from other theories or past research, and it proposes a really clear relationship between the things you're about to study. Let's look at this side by side because it makes it super clear. The aim just states the purpose, to investigate the effect of mobile phone use. It's open-ended. But look at the hypothesis. It makes a firm, bold prediction. Mobile phone conversation while driving impairs driving performance. You see how we moved from just a question to a statement that we can actually go out and test? So, what makes a good hypothesis? Well, it's not just any old prediction. It follows a pretty clear formula. It has to be testable and measurable. It has to state a really clear relationship, and, this is important, it needs to predict the direction of the effect. Is it going to go up or down? It's always written as a statement, never a question. And of course, it's got to be clear and precise. This level of rigor, that's what makes the final results actually mean something. Okay, our blueprint is really starting to come together now. We've got a purpose, we've got a prediction, but now we need the actual building materials for our experiment. This brings us to the core ingredients we're going to measure and change. And these are called the variables.
And a variable is, well, it's exactly what it sounds like. It's just something that can change or vary in amount or in type, and crucially is something we can measure. In any study, variables are kind of like the moving parts of the puzzle. It could be anything. Temperature, how fast someone reacts, a person's mood. The key is, it changes, and we can put a number on it.
So let's break down the three main types using our driving experiment as the example. First, you've got the independent variable, or IV. This is the cause. It's the one thing the scientist intentionally changes. In our case, it's using a mobile phone versus not using one. Then you have the dependent variable, or DV. This is the effect. It's what you measure to see if the cause did anything. Here, that's the number of driving errors. And finally, and these are so important, you have the controlled variables. This is everything else you keep exactly the same car, the same route, the same time of day, to make sure it's a fair test, and you're only measuring the one thing you care about. All right, we've got our purpose, our prediction, and our variables. But there is one last, absolutely critical step, and this is where things get really clever. How do you take a fuzzy, abstract idea like driving performance and turn it into something you can actually count or time with a stopwatch? This next step is maybe the most important key to the whole experiment. I mean, think about it. How do you measure something like driving performance? Or even bigger, how do you measure something like love? These things are totally abstract. You can't just take out a ruler and measure love. So to run a real experiment, we've got to figure out a way to translate these fuzzy concepts into concrete physical actions that we can see and count. And the solution has this brilliant, kind of clunky name, operationalization. All it means is defining your variables by the specific procedures or operations that you use to measure them. It's how you make something abstract totally concrete. And it's so important because it means any other scientist in the world can look at your work and know exactly what you did and how you measured it. Check out how this works in practice. You take an abstract concept, like love, and you operationalize it into something you can literally count, like the number of times someone kisses or touches their partner in an hour. Or you take our driving performance idea. You operationalize that as, say, the number of times the car swerves out of its lane. All of a sudden, these vague ideas become hard, testable, repeatable data points. This right here is the absolute heart of good experimental design. So let's step back. We've built our entire blueprint now. We went from the aim and the hypothesis all the way to defining and operationalizing our variables. But what's the big picture? Why does any of this matter if you're not, a scientist in a lab coat? Because this blueprint, it isn't just for scientists in a lab. And that's maybe the most important thing to take away from all this. This structured way of thinking is a tool. It's a mental model that has huge, powerful uses for making better decisions, for seeing through flimsy arguments, and just for solving problems in our everyday lives. Really, you should think of this blueprint as your personal toolkit for clear thinking. It gives you the power to look at a news headline or some flashy marketing claim, or even just your own deep-seated beliefs and start asking the right questions. It lets you separate the fuzzy, vague ideas from the hard, testable facts. And that's how you turn simple curiosity into real, credible knowledge. So, I'm going to leave you with a challenge. The next time you see a headline about some new study, I want you to look right past that flashy title and try to spot the blueprint underneath. Ask yourself, okay, what was the real aim here? What was the specific hypothesis they were actually testing? And how did they operationalize their variables? You might just find that the answers to those questions are way more interesting and way more revealing than the final conclusion itself.